So in class today we looked at linear inequality word problems. And so just like any other word problems, we're going to try to define our variable, or in this case variables, what we do and do not know. And then with inequalities, there's a few things that we also want to be mindful of. The first one is there just one variable? So just one unknown. And if there's one unknown, we only need one equation, or in this case, one inequality. And we only need one number line. When we have two variables, that means we have two unknowns in our story. We're going to require two number lines, which means we're going to have to graph it. And we're going to need two or more inequalities to do what we need to do. But with inequalities, the two or more part of it will extend as far as many boundaries or limits the problem sets up. So every time we solve an inequality and we get x is greater than or equal to 3 or less than or whatever inequality, we just set a hard boundary on our solution set. We're saying that x is allowed to be any number bigger than 3. I don't care what that number is. As long as it's bigger than 3, it works. A lot of our word problems set up multiple different boundaries. Sometimes 4, sometimes 5, sometimes 6. And when we deal with it out there in the world, this is where the real world application of inequalities pops in. Is we have all these fighting boundaries and we have to find the solution that satisfies it all. For instance, anytime your family decides to go out to eat, take out food, like fast food or whatever, someone's like, I don't want to eat any, like Mexican food, or, I don't want to eat Italian food. I don't want to eat, I don't really want a cheeseburger. I don't really want a sandwich. And all these different things are combining, and then there's something right in the middle that satisfies everybody. Same thing with inequalities. So the first one we're going to start with is the 7th grade class is putting on a variety show to try to raise money. It's going to cost them $700 to rent the banquet hall, and then they're going to charge $15 for every ticket. The sentence we always want to look for in any word problem is that very last one, right there. How many tickets will it take to sell at least $1,000? So how we know that this problem is an inequality is because of this statement right there, at least $1,000. And then this statement right here, how many tickets, is telling me what I don't know about the problem. So x is going to represent the amount of tickets. So here's my amount of tickets, however many that I sold, 10, 20, 30, 100, 200, 500, whatever the number is. And I'm going to get $15 for every ticket I sell. So there, I've charged the $15 for every ticket. I, at one point, spent $700 to get this ball rolling. So I lose that $700 off of my profit. And overall, I want to make sure that I make $1,000 at least. So if we look at this inequality and kind of break it down, here's how much we get for the tickets. Here's any initial costs. And this is what our profit has to be. Now, profit, remember, is revenue minus costs. So I sell a bunch of tickets. I then have to subtract all of my costs before I can actually walk away with the money. So now that I have my equation, my inequality for that matter, not an equation, I can solve this. I'm going to add 700 to both sides. So in order to make $1,000 profit, I really need to make $1,700 in revenue. So this is profit, $1,700 in revenue in order to get that profit. I divide by 15 on both sides, and X is greater than or equal to 113.3 repeating. I'm just going to double check to make sure that was right. That it is. So that means I need to sell at least 113.3 repeating tickets, which we can't sell a third of it. So what I really need to do is I need to sell 114 tickets to make my $1,000 profit. Because we only had one unknown, I only needed one inequality, which led me to one answer that I can put on one number line. So here's 103.3 repeating. It is a closed circle, and I need all the numbers bigger than it. All right, next one. So I have a pipe. It's at least 21 feet long. So let's start with the absolute boundary of just 21 feet. It could be longer than that, but we're going to go with, again, the boundary. That's what we're looking for in all these problems. Because I don't care what happens in between or even at the greatest end. I need to find out where does the problem switch over from being good to being bad. So 21 feet is the smallest I'm allowed to have. So I've counted it for it in my problem, and I'm going to cut it into 3 pieces. The second piece is going to be twice as long as the first piece, and the third piece, my little screen's in the way, I'm going to move myself. The third piece is to be 1 foot longer than the second piece. All right, so haven't said anything about the first piece, so that's what our unknown is going to be. We have no idea about the length of the first piece. So I'm going to put X. Nothing was stated about the first piece. Even when we look at, I need a minimum length of the first piece. Bam. Even proves it right there with our last sentence. Our second piece has to be twice the first piece. And then the third piece has to be 1 foot longer than the second piece. Well, if the second piece is 2x, 1 foot longer is plus 1. So I take all of this. You can see that x, 2x plus 1 are the same as 21. So I can say the first piece and the second piece with the third piece. Whoops, I said third and wrote 3. That's my bad on that one. Has to be at least 21 feet long or greater. So the 3 pieces have to be longer than 21 feet. Combine my like terms, I get 5x plus 1. Subtract both sides from 1. Divide by 5. So what we found here is that the first piece has to be 4 feet long or more in order for the whole pipe to be 21 or more. Plot my result on a number line. Here's 4. It's a closed circle, and I need everything bigger than 4. When we move on to a problem, and I've provided a graph that tells you that there's going to be 2 unknowns. Now, if you're working on something and you don't have the graph, how do you know if you need a graph? Well, see if you have 2 unknowns all the way through the problem. So Sarah's going to buy bracelets and earrings. Right there, that tells me, ooh, 2 very separate items right there. X is going to represent bracelets, the number of them, and Y is going to represent the number of earrings. So they want us to write inequality represent the cost and the number of bracelets. All right, well, the biggest thing about inequalities, especially when you're dealing with two variable, is you want to find what limits the problem. So what's keeping you from just going crazy and buying as many as you want or buying as few as you want? The first one is Sarah can't spend more than $36. So she can't just go to the store and buy 150 bracelets because she can only spend $36 total dollars. So we're going to have a problem that talks about the cost being smaller than 36. Well, the number of bracelets is $2 per each bracelet plus $3 per each earring. That total cost here has to be smaller than $36 here. So there's our cost inequality. But what else limits her is that she has to buy at least 6 bracelets. Excuse me. So that means the number of bracelets have to be greater than 6. So when we graph these two lines, I'm going to graph the purple equation in purple. That's a perfectly vertical line. I know it's not perfect because I'm drawing it. That's the best of my ability right there. And I need all the x's bigger than 6. But then we get limited again for this one. So if we use our tiny table method, so we're going to find our x and y intercepts. We plug 0 in here, divide 36 by 3, and we get 12. We plug 0 in here, divide both sides by 2, and get 18. Connect the dots with a nice line. It's not my best line, but it's okay. And I need everything below this line right here. Oops. So anywhere in this shaded region right there will satisfy both criteria, both limits of the problem. So for instance, I'm just going to pick a point, use my creative pen here, put a little smiley face. Bing! Right there. That point is 8, 3. So that's 8 bracelets, 3 earrings. So it's more than 6. That's good. Check that one off. 8 times 2, that's 16. 3 times 3 is 9. That gives us $25, which is less than 36. That is a satisfactory answer. We move this smiley face anywhere else, you still have a satisfying answer anywhere. Heck, she could buy 16 bracelets and no earrings and still fit the criteria she set for herself. Once you move outside of that region, you are not satisfying one of the criteria. For instance, here, you're under budget, but you don't have enough bracelets. While over here, you have enough bracelets, but you're over budget. Here, you don't have either. So let's try another one. We're going to cross out one of these lines. So this first line right here, I'm going to put a box in. We would have to graph it because it's a limit to the problem, but we're just not going to include it at all for the purpose of this example. So we're playing basketball, and it looks like we have X is some number of 2-pointers that we've made the field goals, and Y is the number of 3-pointers that we make in any given game. So it looks like we've scored at most 30 points in a game. So in a game, we've never scored more than 30 points. But I've made at least 3 2-pointers. But I've never made more than 5 3-pointers. So what helps in word problems a lot is to look at the units. So when we look at this, 3 is really talking about 2 pointers. So I need to be talking about X. 5 is talking about 3 pointers, so it's talking about Y. Now 30 overall points, if I just write this statement right here, that statement is saying that the number of 2 pointers plus the number of 3 pointers has to be less than 30 points. Unfortunately, the units don't match up. The number of 2 pointers, the number of 3 pointers don't give us 30 points. This would tell us the number of baskets, of total baskets, which then we could probably do some math to find the points, but it doesn't tell us the points directly. So what we can do is add in that we get 2 points for every one of these baskets, 3 points for each one of these baskets, and all of a sudden the units kind of fall into place. This is now talking about points, this is talking about points, and this is talking about points. Everything lines up. Where before it was just the number of these baskets, the number that we make, were supposed to equal points. And that's not true. Just because you know, it's like, oh, he made 10 2-pointers. Well, you need to know times that by 2, and that's how we get our equation up there. All right, so now we're going to graph what we have. Top equation right here, find our x and y intercepts. So we plug 0 in for x, we get 10 for y, 0 goes in for y, and we get 15 for x. So that's our point line. We scored less than 30 points. Then our 2-pointers, we scored at least 3 of them, but we didn't score more than 5 3-pointers. So in a given game, actually we're going to go yellow. A given game, the number of baskets of each kind I made is in this yellow highlighted region. So again, I could have this 5 2-pointers, 3 3-pointers, and that would fit all 3 of these inequalities over here. I could move this dot, I could be way over here. 13 2-pointers, but only 1 3-pointer still satisfies all 3 of these inequalities. It's the minute when I move this dot outside of that shaded region where I'm no longer satisfying all of the criteria. And I need to satisfy all of the limits. So for instance, if we had included this last one, we would have had a 4th equation where we had to score over 6 points. So that would have given us 2 on the y-axis, 3 on the x-axis, and over, and you would have seen that it's that same region. That's why I discounted the line. It's not necessary, because we would shade and then it would overlap right there. Then the last one I want to look at, the radio station's giving away tickets. They're giving away $11 tickets and $16 tickets. They have to give away at least 14 tickets. That's one of those limits, one of those boundaries. At the end of the day, they better have given away 14 total tickets. But they have a contract, and they're not allowed to give away more than $220 worth. So if we look at these two equations, the bottom one's all about the money, the top one's all about the amount. So let's get our 2 variables defined. X is going to be the number of $11 tickets, and Y is going to be the number of $16 tickets. So the top one, since it's just the amount of tickets plus the amount of tickets is going to be the amount. So this top one, the amount, the amount, the amount. The units go all the way across and they fit perfectly together. Like, okay, that's our amount problem. The bottom one's all about the money. So if I just had X plus Y, then I'm still just talking about the amount related to the money. That doesn't line up. So I have to change this side to now be more about the money. Well, $11 times the amount, that's now the money for these tickets. 16 times Y is now the money for this amount, and now everything's talking about money. When we graph this, we do the amount one in blue. My X and Y intercepts are here at 14. Oh geez, that was a terrible line. Better, not good, but better. I need more than 14 tickets. So I'm allowed to give just 14 of either kind exactly, or a combination of them. So for instance, like right here, that's 18 and 15, so that's 33 total tickets. But I can't give away more than 220. So when we make our tiny table, we get 13.75 and 20 as our intercepts. So based purely on money, the most I could give away of $16 tickets is 13 and 13 3/4, or 20 $11 tickets. But I can't give anything more. I would shade below. So our solution set is in between these two lines. So in between those two lines will allow us to give more than 14, but less than $220.